Joining the Teams meeting. All right, so we can all see, oh, it's not the line. The top part's a black bar anyways. Okay, so we are going to go through some sequential logic timing examples. Your quiz next week on Wednesday will be on sequential logic timing. So it'll look like your homework that I've posted, and we're going to be going through problems that look like the homework. So just as a reminder of our timing equations, we have two constraints. We need to satisfy the setup time. That is, our input signal needs to be stable before this setup amount of time of the clock edge. And our equation is this one. We have to go through the flip-flop of the coming out from R1 and then through the combinational logic. And we also need to make sure that we have that setup time in order for it to capture. And then we have the hold time. So the hold time is the amount of time that we need to make sure that our signal is still stable after the clock edge. So we have to make sure that the contamination from this flip-flop and then from this combinational logic doesn't change or start changing the inputs before the whole time is over after the clock edge. And then we had the skew. So we use worst case scenario for skew. So for the setup time, we have to add skew. And then for the hold time, we're subtracting the skew. Because now we're saying that we need to make sure that this takes even longer in the case that it comes late. All right. So here is an example. And this is so it gives us these things. We want to calculate what is the maximum clock frequency for reliable operation. And then what is the amount of clock skew the circuit can tolerate if it needs to operate at 5 gigahertz? And then how much clock skew the circuit can tolerate before it experiences a hold time violation. And then it gives us the timing for the different gates as well as the flip-flops. So what we need to do is, let's just answer this first question. What is the maximum clock frequency for reliable operation? The equation that we need for that is for setup time, because we basically set our clock period to be long enough to accommodate the longest path. So let's find this longest path. So we have many different paths here. Let's just do one at a time. So we have A to X as one of these paths. So if we go A to X, the first thing in our equation is going through the flip-flop, right? So we have 35. That's TPCQ. And then we're going to go through a NAND gate, an OR gate, and an inverter. So NAND is 20. So 35 plus 20 plus what's our NOR is 30. And then our NOT is 15. And then what's the last thing I need to include? The setup time. Setup time is 30. So this is for the path A to X. What is this? I have that it's 130. Is that right? The other thing we need to check is A to Y. So A to Y, again, 35 from the flip-flop TPCQ. And we are again going through the NAND gate. So that's another 20. And then we go through an XOR gate. So that's 60. And then again, setup. It's 30. And this is 145 picoseconds. So this path is longer. So this one is currently what's defining our maximum clock rate. Because if we satisfy this one, we're satisfying this one, right? And then B to X is the same as A to X, right? So B to X, it's just 130. B to Y, it's just the same as A to Y. So B to Y is 1. And then C to X, this one is different. It's just the NOR and the inverter and the flip-flop. But we know that it's less than A to X, right? So we can just say that this is less than A to X. So we don't need to do it. And then C to D, I mean C to Y, is again, we can just say that C to Y is less than A to Y, because A is going through that additional NAND gate. Do you see that? So that means that our F max is 1/145 picoseconds. Because if we have this as our cycle time, our equation of our cycle time is greater than the propagation, well, TPCQ, propagation clock to Q, plus our propagation delay, which is this, well, not that one, but this one, and then plus setup, right? So we need to be greater than or equal to this. So 145 is the number we have. So we see how we check all of these paths. Whichever one is the longest is defining our maximum, well, our minimum cycle time, our maximum frequency. Okay, so the next question is, what is the amount of clock skew the circuit can tolerate if it needs to operate at 5 gigahertz? So the first question is, what is the cycle time of a clock of 5 gigahertz? Well, it's 1 over the frequency. So it's 1 over 5 times 10 to the 9. This comes out to 200 picoseconds. Right? Yeah.
setup, just the maximum time it was asking for. We use the setup equation, right?
Yeah, this is the setup equation. So we were looking for this. Which one is the maximum path? And then when I was looking for that, I was just also adding setup and clock to queue. Right? Okay. So this is our operating frequency. So the 200 is greater than 145, right? So all of our timing equations are satisfied by 5 gigahertz, right? So then the question is, what is the maximum clock skew that we can tolerate? Well, what do we need our time to be greater than? So we need cycle time greater than or equal to 145 picosecond, right? And this is skew, right? And our cycle time is 200 plus T skew. And that means that it needs to be less than or equal to 55 picoseconds. That's our maximum clock skew. So comparing the clock from here to here, the maximum difference can be 55 picoseconds. Right.
What is the skew again?
So the clock, even though it's from the same place, the wire to get from here to here is different. They don't actually arrive at the same exact time. So the skew is just the difference in time of it arriving at these registers versus these registers. Yeah.
Follow the equation. Yeah, that one. So the propagation delay for the clock is the 35, and then the 20, the 16, the 30 is the propagation delay.
Yeah.
So the-
Because it's the time going through these gates.
So if you just added the T setup just because you're just running that.
Yeah.
It's not part of the. Like none of the numbers are the T setup, right?
Here, added T-sun as 30. Because I can find propagation delay on its own. Or I can add this and this and then find the maximum. It's the same thing.
So it's the propagation delay through the flip flop and then the propagation delay through the gates
Mhm.
and then the setup. The other flip flop or
Mhm.
okay.
Because we need to get from the output of the first flip flop. So input comes. And we need to go from the output here all the way to the input here. Okay? So we have to go through the flip flop, which is the PCQ, and then through this circuit. So that's our PB. And we just found the maximum path, right? And then in order for this flip flop to capture that input properly, then the thing needs to arrive early by setup time. Yeah. And then we're going to do the hold time now. So we haven't handled hold time yet. So the question was how much clock skew the circuit can tolerate before it experiences a hold time violation. So our hold time violation, our equation is T hold needs to be less than our T contamination clock to Q plus T contamination delay, and then we have minus skew in case the clock comes late. Because if the clock comes late for these registers over here, then we need to make sure that our contamination delay is even longer. Because the hold time hasn't even started yet if it comes late.
Short, right?
This is the shortest path with contaminations as well. So you're not using propagation, you're using the contamination delays. So our shortest path, what is our hold time first? Hold time is 10 picoseconds. So 10 picoseconds. And then clock to Q contamination is 20. And then our shortest time is, what are we going through here? If we go through the XOR gates, it's 40, that's too long. I think it's going to be C, yeah, C to X, because C we go through the NOR and then the NOT gates. And that is going to be 20 and 10, whereas the XOR is 40 alone, right? So we have contamination delay is 30. So without skew, we're satisfying the whole time constraint, right? 50 is greater than 10. But now we're asking if we add skew, what is the maximum that it can be? Well, T skew needs to be less than 40 picoseconds. If it's any greater than 40, then we have a hold time violation. Yeah.
If it's equal to 40, do you still have the whole time?
Yeah, because this one is less than.
Okay.
Yeah. The other one is greater than or equal to. So we see how to do this kind of question. We worked with clock skew and without clock skew. All right, so for now, what I want you to do, and you can talk to the people around you. You don't have to do this on your own at first. I want you to work on this question. And when you guys are done, can you answer the poll? Any answer just to indicate when you're done. Just don't pull this up until you're done working together. 832. 832. And then we'll go over this.
I have a quick question about the two skew times.
Mhm.
So for the maximum clock skew to operate at 5 gigahertz has to be great. Oh, sorry, less than. So the range of our skew is between 40 and 55. That's like tolerable then?
Did I write it wrong? No, yeah, clock skew still needs to be less than 40. Less than. They're both less than.
Oh, both less.
One is just less than or equal to.
Okay, got it.
So really the bound is the 40 to have no violations. But they're kind of on different ends because the hold time the clock is arriving late. Whereas the setup time, the clock is arriving early. And then this one announced. That's, we have this kind of path that we haven't seen before, where we're going from this register, skipping a register and going into this register. We have this. But it's the same concept. You have to look at every register to register path. Which one is the maximum propagation delay? Which one is the minimum contamination delay?
Yeah, my God.
Oh, yeah. Don't forget.
I think.
Let's see, somebody, that needs to be, we will assist out there, so you can get something like this. Sheesh. Yeah.
Was there the last one?
Yeah. That's my final. Actually. No. You see who's happening. Oh, no, but it's.
Okay, so we do a. Then this is P. Then this is set up. Well, no, because we're going for the longest path.
Yeah.
Thanks, Jamie. Like, did you do it here? The split yesterday is putting off like all of those things too. This was pretty. Easy with the whole thing. You said.
Yeah, I think we just.
But you did include the publication.
Oh, yeah. For the whole surgery. Justin Phil. Or the biz are we none of them receive any waveforms, so it's to calculate something else, or it's gonna be distant. So you think we made the. Because usually taught us we should have waveforms on the grid as and stuff, so you should add it up.
Might be two problems, but one is definitely going to be this.
Okay. That's the minimum. Unless there's. How much is that? That's the control. Yeah. Yes, that's. Five. Well, you can just get that little tiny part. But that's. We can't be saying. It's all nice. I don't know, tell small size again. Having super small with something that they becoming.
Yeah. Like how small. This could be on the big.
What's next? Yes. So it's like.
We have, my grandson, they're not very showing bunch, but it's hard to. No restriction. But it knows. Yeah.
That's just.
Oh, we're doing contamination. So the shortest path is.
Which one?
So I can have.
Yes.
Well, I was thinking about it, but this is.
All the defense of the.
But then now, what we need is to buy. Oh, I just, we're gonna find my hole from here. We're gonna both know if we stay where you find this. That's probably the truth. So this reviews, for example, like 3 to 5 volts to 6 volts. And that's the control. Okay. You go I mean, I don't have to be on people. I mean, it's like, whether they're back here, they're caught, or they has to be funny, like, I'm seeing, it's like, hoping it to be less than. It's even more, it says, I'm worried about it, I guess it's like, so.
So I call.
It's more accurate. Oh, I see, I see. No, you know, it's fine. It's fine.
Okay, so I hear discussion diverging. I think some people are still working, but also in the interest of time and to get through this this problem. And then the last problem I'll just leave on the slides. You guys can do on your own at home or wherever. But let's do this one together. So first part, calculate the minimum clock period for the circuits. So which equation are we using? Setup time. Yep. So just as a reminder, setup time, I wrote it on the next slide. So my cycle time is going to have to be greater than or equal to the time for the propagation clock Q of the flip-flop, the propagation delay of the circuits, and then set. So this and this are the same. Are flip-flops. We need to find the maximum of this, right? So we're looking for the longest path in terms of propagation delay. By which path do we like to look at? Next to B is not interesting, right? One gate, and it's a not gate. We don't really have to look at this, right? So what's the path form we should look at? A to D, is that interesting or not? It's also one gate, right? So where are contending paths? We can start at X. To where? To D? Or you know over here, this D, the top three. That's a contending path. Right? So X. So what is this going to be? So the nodes is 10. So 10. And then NOR 15. So we're at 25. And then more. So this is 50. Right? It could be. But let's also look at what about from Q here, from after the first flip flop. It's also here. Because this includes the clock to Q flip flop, which is 50, which is certainly longer than 10. And then it follows that same time. So 50, 15, so 65 plus 25, so 90. Okay. So that's long. For 90 versus 50. And this one is the longest path. Q from flip flop 1 outputs to flip flop 3 inputs, all in that path. So
R.
Yeah.
Y is from input X to output Z through all the flip flops, not
this
this
one
choice.
doesn't go to flip flop.
So
There's no flip flop at the end.
we
So
just
we don't
want
care
from flip flop
about
to flip flop.
we don't care about how long it takes to get here because it's not being captured.
Okay.
There's no setup time to be considered. We're only looking at flip flop to flip flop.
Okay.
All right. So we have then. So clock to Q was 50, and then the propagation delay of the, what is this? The NOR was 25 plus the, oh wait, the NOR was 15. So 15 plus 25 for the OR. Right? And then that gives us, so T. This is our minimum clock period. Right? So the next question was, assuming that the flip-flops have hold times of 20 nanoseconds.
Just
For, yeah.
when it says all gates have a 10 nanosecond contamination delay,
Mm-hmm.
we don't add that to the.
No, contamination delay is different than propagation delay. So we're going to use contamination delay now. So hold time of 20 nanoseconds for first two flip-flops, 200 for the third flip-flop. So we're going to check our hold times for all of these flip-flops now. So T hold needs to be less than R T contamination clock to Q and contamination delay. So let's do D flip-flop 1, D flip-flop 2, D flip-flop 3. So this one was 20, this one was 20, this one was 200, right? So if we look at flip-flop 1, we just come from one place, right? X through the NOT gates into the input. Right? So there's no contamination clock to Q. It's not coming from a register, right? And then our contamination delay for every single gate is 10. So for the first flip-flop, we have hold time violation. Right? So this is no good. Second flip-flop. We have two paths from X. Let me swap to laser pointer from X to here, and then from here to here. And then again, we have all gates are 10 nanoseconds of contamination delay. So we have 10, 10, so 20 for this path, and then clock to Q. It's just another, it's 10, and then 10, so it's 20. Right? So D flip-flop 2, we are also unhappy. Because 20 is not strictly greater than 20. So we also don't like this one. And then we have D flip-flop 3. So flip-flop 3, our shortest path is from flip-flop 2 to flip-flop 3, right? So because if we go from A or X, we have 1. So this would be 1, 2, 3. And then from it, this would be 1, 2, 3. But if we just go from our output here, it's 1, 2. So this is again 20. So we also don't like that. So all three of them have hold time violations. And we are going to fix that, right? So now you have access to buffers that have 20 nanoseconds of delay each. Use the buffers to fix the timing violations of the circuits. And then we want to calculate the new minimum clock period. So I need, let me switch colors. I need one buffer here. Okay. I need one buffer here. I need 10 buffers here. All right, so now we need to decide where are we putting these buffers. So for the first one, we have no choice, right? It goes right there. That's the only path. For the second one, because of this buffer from the first one, this is now 1, 2, 3 for that first path, so we're good, right? But here we still have 1, 2, so we need to insert our buffer here. Yep.
You, then you have second gate, you get to the second flip-flop. Do we no longer consider Q as 15 nanoseconds?
It says all contamination delays are 10. So the clock to Q here. This is 10, this is 10, so it was 20. And then this is 10, this is 10, so that path was 20, so they're the same. But the buffer from the first one fixed that first path. And now we just have to make sure that we add this buffer to fix the second path. So that covers flip-flop 1, flip-flop 2. Now we need to do flip-flop 3. So our path was, which one was our path? All right, so B to D. So this is our main problem. So because we have 1, 2, so we need here we need 10 buffer. No, we don't. Yeah, we still need 10. So let's try and see if we can sneak them here first, because we don't want to modify our longest path too much. So if we put not 20 of them, I wanted 10 of them. So that solves that path, but we still have to consider the other paths, right? So if we go from, here's my lid. So this is 10, 30, 40, 50. I still need buffers here, right? Because what did I say this was, 50? Yeah, so I would still need 8 buffers on this side, right? To satisfy this path. Because we still have to satisfy all the paths for contamination delay.
Oh, we make that path.
Yeah, so rather than putting 10 buffers here, because I need 8 buffers here, I can put 2 buffers here, 8 buffers here. So let's do that. So let's change this to 2. Let's put 8 here, and now it satisfies both of those paths. And let's just make sure that we're still good with this. So this is 10, this is 20, so this is 30, 40, 50, and we still need 8. So all of our paths are good now. So those are our inserted buffers. The last part was, what is the new minimum clock period? So we've modified our data path by a little bit. So our 2 contenders are still X to D flip-flop 3 and A to D flip-flop 3. So if we go from X, we have, so X to flip-flop 3, we have 10 for the inverter. Then we have 20 for now this buffer. And then what was the NOR gate? 15, right? And then 25 for the OR gates. And then we have 8 buffers. So that's 160, right? So what is this? Is it 230? 10? Huh? Okay. Then we have A to flip-flop 3. So for A, we have 50 for propagation clock to Q. Now we have 20 for that buffer. And then the NOR is 15. The OR is 25. And we still have those 8 buffers at the end. So this is, yes, but what is it? It's not 350. That's too large.
310.
Okay, do I have to do this? 40, right? So this is 200, 270, right? Yeah. So our new minimum clock period is 270. And what is our unit for all this? Oh, great. So let's just imagine all of these were,
Oh, something kind of.
Yeah, I think it's a typo anyways. So 270 picoseconds. So that's how we go about these problems, right? So if you have these violations in terms of hold time, you add buffers. If you have violations in terms of setup time, you make the clock period longer. Right? So this one I will leave to you guys to do. Your homework looks like this one. You don't have to do as much look at all of the paths. It just tells you for this path from this flip-flop to this flip-flop, this is the propagation delay, this is the contamination delay. So then you're just trying to find the just have to find the maximum between them all, right? And then for contamination, it's the minimum. So yeah, the poll was, what was it? 832. 832.